Hi, my name is Emma Yang. I'm from the talk Tackling Cancer with the Wolfram language, and I'll be talking about a lung cancer detection project I'm working on. So hi, I'm Emma. I'm a mentorship student in the Mentorship Program, and I'm going to be talking about the program, some projects I've done in the past, and then a lung cancer project I'm doing right now. So first off, let me share some of the how it works with the Mentorship Program. So I've been working with projects using the Wolfram language and to kind of learn about data science and other things I'm interested in. I've been meeting weekly with my mentor, Andrea, to kind of guide me through my project and tackle any issues I'm having. So let me show you some of the projects I've been working on. So last year, I participated in something called the Opportunity Project, which was run by the White House. And it was to use open data to create a tool to map out summer meal sites for students who need it. And so I used open data through the Wolfram data repository to do that. And then, let me see. Over the summer, I went to the high school summer camp where I worked on a machine learning project to identify road signs. So now I'm going to talk about the lung cancer project I'm working at right now. So it was inspired by a data science competition on Kaggle, which is a platform for people to share data sets and hold competitions. And their data science goal this year was to improve lung cancer detection. So I wanted to use how much data there was available to kind of learn more about data science and machine learning. So let me talk about a little bit of the data that was available. So the first one was data that Kaggle provided by themselves, which included over 1,000 patients worth of CT scans, and each of them was marked with whether or not they had cancer. But then through the forums, I also found a data set called Luna16, where you not only have whether it has cancer, but you also have the location of the nodules or the tumors. And then that's a subset of an even larger data set called LIDC IDRI that has just nodule locations and then also some characteristics about those nodules, such as malignancy and their size. So I have tried a couple approaches. I'm going to walk through some of them. The first one was to directly implement an approach I found on Kaggle through a tutorial, which basically was to train a segmenter to zoom in on an area that was suspicious and then use a cancer classifier to see whether that area was cancerous or not. So what I found was that classifier can't take 3D images, so I had to take a 2D approach. And then I also found that a lot more pre-processing was needed than just putting it in the classifier in order to kind of specialize the classification approach. So after this, I tried feature extraction to see whether I could create a more specialized classification approach. So the first one I tried was to use the rate to quantify kind of the shape of the lung by taking the ratio of black pixels to non-black pixels, and to see whether we could cluster the images by what kind of shape. So you can see that for the more regularly shaped images, it works fine, but when you get to more irregular shapes, it kind of gets confused, especially with more irregularly shaped lungs. So I wanted to see why that was. And so I did a feature space plot, and we found that each of the curves of each patient is slightly different. And so it's hard to pinpoint exactly a direct way to kind of cluster the shapes of each lung. So now I'm working on this, like the current approach I'm working on is based off of one of the winning solutions of the Data Science Bowl, which recently ended. And so what I'm doing first is to normalize all the data and the scans through cropping them, because you see there's all this blank white space that could be potentially confusing the classifier. So I wanted to, if you want to take that away, you can take a look at this pixel spacing attribute, and which is found in the metadata of each 2D slice. And you can see that for this one's 0.703, and you can crop that down to those image dimensions and crop out most of the white space. And then after that, I wanted to create my training data. So what I did is that I got each CT scan, the 3D image, contains an XML file, and that contains all the data about nodules, whether they're cancerous or not, and their location and some characteristics about them. So I used mostly the Z position of the nodules, which shows you how high or low in the lung it is, to connect that with Z positions in here, which you can see with an image position, and match whether that 2D slice contained a nodule. And you can see that if it's false, that means it doesn't have any nodules. If it's true, then that means it contains nodules based on this data. So the step I'm working on right now is to take a look at which of the neural networks is going to be most suitable for training with my data. So the first one, I'm using NetModel to get some of the different models that I could use with an image classification. And right now what I'm working on is testing those out and seeing what happens. For me, the next steps are going to be further honing my model to include some of these characteristics, such as the malignancy, the diameter, which is how big it is, and then some data about the structure of the nodules. Just take a look at whether those will further enhance the model and see whether those make it more accurate. So I'm going to go through some of the biggest challenges for me. So one of them was to find the right way to represent the data. So I've found various approaches through the Kaggle platform. Some of them involved making an actual 3D image out of it and training as a bulk. And then some of them involved just training as 2D images all separately, or 2D images kind of grouped together. So finding the right way to represent the data based on my approaches and what I wanted to try was one of the biggest challenges for me. And then afterwards, also trying to find the right way to classify or model the data. For example, we first tried clustering, and then in order to do feature extraction, now we're going to do image classification. So finding the right balance is also something I'm working on. And then lastly, finding the right steps to accurately model the patterns in the data. So the first one we tried was a segmenter and a cancer classifier. And then with the feature extraction, we tried a shape and a cancer classifier. And now we're doing a more nodule-based, location-based classifier. So I'm still trying to find which one is most suitable and which ones I could mix and match to make sure that we cover all the bases. So my goal for this is to build a model that can accurately predict lung cancer, and then maybe down the road I could deploy it in a real-world scenario. Thank you.